So, welcome to the 1948 Nobel Prize in Physics, another one that really stands on the shoulder of giants, but it does more than that. This one went to Patrick Blackett, who, among other things, was a British lord. He served in World War One. I mean, there could be entire videos about this man and his life and his achievements. But one of the things he did achieve was he won the Nobel Prize in 1948. The official announcement said it was for his development of the Wilson cloud chamber method and his discoveries therewith in the fields of nuclear physics and cosmic radiation. It's a big fancy way of saying a whole lot of things all in one sort of short, tight sentence. We'll cover all that in a minute. But what he did was he used some new techniques with some older instrumentation to really massively increase the sensitivity. And what that did was it helped out the nuclear physics teams and the astrophysics teams all at once because they had this new instrument to go work with. And he did a lot of that work as well. Now, he did that to a cloud chamber, and his work was really done in 1932 that he won the prize for. But it was an experiment done on some equipment that was really the basis for it was the work that Charles Wilson had done, who won the Nobel Prize in 1927 for his first use of the cloud chamber in a scientific lab. And if you remember, Wilson was not only a physicist, he was also a meteorologist and all kinds of things. So he really did take an old idea, put a new twist on it, make it even better, and for that he was awarded the Nobel Prize. One of the many things about him in his scientific career that I think are notable and worth mentioning before we dive into the details of what he did and how he did it was he had a bunch of students over the years that he taught different things to, some of which you've heard of, some of which you haven't. But one of his notable students was actually Robert Oppenheimer from the movie that took basically every Oscar it was nominated for home last year. So Oppenheimer actually learned a lot of stuff from this guy when he was a student. So with that, let's dig into Patrick Blackett. And what you see here are tracks left in a cloud chamber with both alpha and beta particles. Don't worry about what those are, but that gives you an idea of what these early cloud chambers looked like. Now, remember from the previous video on Wilson, who won the Nobel Prize for his work in cloud chambers, that the cloud chamber itself is just an instrument that uses electrically charged particles as they pass through a super saturated pile of air to study the trails that they leave behind, just like the ones you see here. Now, in this case, they used the cloud chamber to break new ground in the study of cosmic background radiation as well for cosmic rays, as well as nuclear reactions. Now, this is very much what his lab looked like when he was doing these experiments. This is probably, in fact, a cleaned up version of it for photographs they did after the fact. But science labs, when you're doing the first of something, have a tendency to be a little bit goofy looking, and this one takes no exception to that. But in 1932, Blackett and Giuseppe Alcalani connected the cloud chamber to a Geiger counter, and that allowed the detection of passing particles to be detected very easily, and that allowed them to automate a method of taking photographs at the precise moment the particle passed by. This allowed many different experiments to be run, and he proved, among other things, that with the application of high amounts of energy, pairs of electrons and positrons could be formed from photons, which was very new information at the time. These types of particles being formed by nuclear processes was new and is still something that physicists are studying to this day. So particle physics is still very much an alive and well field. Now, if you want to learn more about the nuclear process that forms other types of particles or new types of things, I suggest watching the Nobel Prize video on Enrico Fermi, who did all sorts of that kind of work, and I went into detail on that in that video. But what are cosmic rays? Now, cosmic rays are things that originate in the sun, or perhaps from outside of our solar system, inside our own galaxy, or maybe even from distant galaxies or from black holes. But what they are is particles that are moving through space. They produce, and in general, not many of them hit the surface of the Earth. Some still do, and they can be picked up by laboratory equipment. In fact, they can throw lots of error into your experiment if you're not careful. You may detect something, you think you see a nuclear process, and it's really a cosmic background ray. But you do have to account for that, and the way that's done is usually by taking some sort of background of your lab and getting that and filtering it out of the main signal, so you know exactly what you're doing. It's called calibrating your equipment. Now, cosmic rays are generally blocked by the upper atmosphere. That's one of the reasons we're kept alive, because our atmosphere protects us from these things. But they can produce showers of secondary particles, some of which do reach the surface of the Earth. So when we are picking up cosmic rays, sometimes we are picking up the actual cosmic ray. That's very rare, but usually what we're doing is picking up those secondary particles. But even those secondary particles can wreak havoc on a lab if you really want to get solid measurements. So those things are important. And also it is a way for us to track whether or not we have increasing problems in our atmosphere if those actual cosmic rays make it through instead of the secondary effects. So think about this prize another way. Yes, he formed a lot of new things, just like Fermi did and others. And I urge you to watch that video as well if you're curious about how particles are formed. But he learned a lot about the cosmic background, so those cosmic rays that come in. And normally our atmosphere does shield the majority of them, and that was new information. And really what he worked out was also that, yes, as they're stopped by the magnetosphere and the ionosphere and other things, what we're measuring are secondary particles that come cascading down from our own upper atmosphere. And even some of those are reflected off into space. But what's important to know is that we understand that radiation is there. We understand that background is there and has been since sort of the dawn of time. But what this does is it tells us another way to actually monitor our own environment and see, is there really a shift going on? Is there a change in the upper atmosphere? And how can we really work backwards to see exactly what that change is? We don't necessarily need to run up to high altitudes and take gas samples. We can do it in a secondary effect and tell very closely to what's going on up there. So what this sort of science does is it gives us another set of tools in which we can better understand the planet we live on and outer space all at the same time. And this is the sort of thing I'm talking about when I say, hey, look, fundamental science can really change our understanding of our world and tell us what we are either doing right, doing wrong, and help us really kind of move forward. But it has to be done at this fundamental level. True understanding can't come from this sort of, hey, look, we must look at this thing one way or another. We must look at science objectively. Otherwise, we're just kidding ourselves. So this prize was fantastic in the fact that it taught us a lot about even our own atmosphere that we didn't necessarily know at the time. So we'll see you on the next video. Please don't forget to click subscribe and like, and we'll see you soon.